Good morning students. Welcome to 11th standard chemistry video class. In this video, we have to start with the new lesson. Lesson 9 Solutions. It is present in your chemistry volume 2 book. In this lesson Solutions, first we will start with the introduction part. Introduction. Many chemicals that play an important role in our daily life. All the chemicals are in different physical forms, namely solid, liquid and gas. Most of the chemicals are in the form of mixtures and rarely as pure substance. Generally, most of the mixtures are homogeneous. Such homogeneous mixtures are called as solution. Again I repeat, generally most of the mixtures are homogeneous. Such homogeneous mixtures are called as solutions. Seawater is an example for solutions. Here 70% of Earth's surface is covered by seawater. It contains many dissolved solids, mostly NaCl, that is sodium chloride. Air is also example for solution, where air is a homogeneous mixture of the nitrogen, oxygen, carbon dioxide and other trace gases. Brass is homogeneous mixture of copper and zinc. From the above, it is understand the solutions are in different physical states, namely liquid, gas and solid. For liquid, it is seawater. For gas, it is air. For solid, it is alloy. Homogeneous means uniform distribution of the components throughout the mixture. In this lesson, we will discuss solution and their properties. First, we will start with types of solutions. Types of solutions. A solution is a homogeneous mixture of two or more substances consisting of atom, ions or molecules. Solution contains solute and solvent. What is solute and solvent? A substance which is present in large amount in solution is called solvent. The substance which is present in small amount in the solution is called solute. In sodium chloride solution, small amount of sodium chloride is dissolved in water. Here NaCl is solute where water is solvent. Solution is classified into two types based on solvent, namely aqueous solution and non-aqueous solution. Solution in which water acts as a solvent, it is said to be aqueous solution. Solution in which other than water acts as a solvent is said to be non-aqueous solution. It may be benzene, carbon tetrachloride and ether. That is, other than water, the solvent used may be benzene, carbon tetrachloride and ether. Next, let me discuss different types of solutions based on the physical state of the solute and solvent. Types of solution based on the physical state of the solute and solvent. This tabular column contains state of solution, solute, solvent and example. Here we are having three different types of solutions, namely gaseous solution, liquid solution and solid solution. First, we will start with gaseous solution. Here gas solute is dissolved in gas solvent. For this, the example is air, where air is a mixture of nitrogen, oxygen and other gases. Next, liquid solute is dissolved in gas solvent. For this, the example is humid oxygen, which means oxygen containing water. Next, solid solute is dissolved in gas solvent. For this, the example is camphor in nitrogen gas. Next, we will discuss liquid solutions. Gas solute is dissolved in liquid solvent. For this, the example is carbon dioxide dissolved in water, that is carbonated water. Next, liquid solute is dissolved in liquid solvent. For this, the example is ethanol dissolved in water. Next, solid solute is dissolved in liquid solvent. For this, the example is salt water. Finally, solid solution. Gas solute is dissolved in solid solvent. For this, the example is solution of H2 in palladium. Next, liquid solute dissolved in solid solvent. For this, the example is amalgam of potassium, which is used for dental filling. Next, solid solute is dissolved in solid solvent. For this, the example is gold alloy of copper used in making jewelry. Hence, we completed different types of solution based on the physical state of the solute and solvent. Next topic, expressing concentration of solutions. In our life, we have come across many solutions of varying strengths or concentration. Substances like mouthwash, antiseptic solutions, household disinfectant are expressed in mass by volume percentage. ppm is used for TDS of water. Here, ppm is nothing but parts per million. Laboratory reagents are expressed in molar and normal to express the concentration of solutions. Here, the concentration of solution gives the amount of solute present in a given quantity of solvent. Next, we will discuss the different concentration terms and to prepare a solution of specific concentration. Different concentration units and their illustrations. First, we will discuss molality. Molality is expressed as number of moles of solute divided by mass of the solvent in kilogram. Here, number of moles of solute is given by mass of solute divided by molecular mass of solute. It is explained here. The molality of the solution containing 45 gram of glucose dissolved in 2 kg of water. Here, the solute is glucose, the solvent is water. For this, the molality is given by number of moles of solute by mass of the solvent in kilogram. Already, we know that number of moles of solute is equal to mass of solute by molecular mass of solute. The value to be substituted in this expression. We will get 45 divided by 180 whole divided by 2. Here 45 is the mass of glucose, 180 is the molecular mass of glucose, where 2 is the mass of water. Therefore, 0.25 by 2, which is equal to 0.125 m, where m is molality. Next one, molarity. Molarity is expressed as number of moles of solute divided by volume of solution in liter. Here, number of moles of solute is equal to mass of solute divided by molecular mass of solute. It is explained here. 5.845 gram of sodium chloride is dissolved in water and the solution was made up to 500 ml using a standard flask. Here the solute is sodium chloride. The solvent is water. Therefore, the strength of the solution in molarity is given by number of moles of solute by volume of solution in liter. We know that number of moles of solute is equal to mass of solute divided by molecular mass of solute. Here the values to be substituted in this formula. We will get 5.845 divided by 58.45 whole divided by 0.5. Here 5.845 is the mass of sodium chloride, where 58.45 is the molecular mass of sodium chloride, where 0.5 is the volume of solution in liter. After simplification, we will get 0.1 divided by 0.5, which is equal to 0.2 m. The m represents molarity. Next one, normality. Normality is expressed as number of gram equivalents of solute divided by volume of solution in liter. Here, number of gram equivalents of solute is equal to mass of the solute divided by equivalent mass of the solute. It is explained here. 3.15 gram of oxalic acid dihydrate is dissolved in water and the solution was made up to 100 ml using a standard flask. Here the solute is oxalic acid dihydrate. The solvent is water. The strength of the solution in normality is given by number of gram equivalents of solute divided by volume of solution in liter. The number of gram equivalents of solute is given by mass of oxalic acid by equivalent mass of oxalic acid whole divided by volume of solution in liter. The values to be substituted here. 3.15 divided by 63 whole divided by 0.1, where 3.15 is the mass of oxalic acid, where 63 is the equivalent mass of oxalic acid, where 0.1 is the volume of solution in liter. After simplification, we will get 0.05 divided by 0.1, which is equal to 0.5 n, where n represents normality. Next one, formality. Formality is expressed as number of formula weight of solute divided by volume of solution in liter. Here the number of formula weight of solute is equal to mass of solute divided by formula mass of solute. It is explained here. 5.85 gram of sodium chloride is dissolved in water and the solution was made up to 500 ml using a standard flask. Here the solute is sodium chloride, the solvent is water. The strength of the solution in formality is given by formality is equal to number of formula weight of solute divided by volume of solution in liter. Here the number of formula weight of solute is given by mass of solute divided by formula mass of solute. The values to be substituted here. 5.85 divided by 58.5 into 0.5 liter. Here the 5.85 is the mass of sodium chloride, where 58.5 is the formula mass of sodium chloride, where 0.5 is the volume of solution in liter. After simplification, we will get 0.2 F, where F is the formality. Next one, mole fraction. Mole fraction is expressed as number of moles of the component divided by total number of moles of all the components present in solution. Here X represents mole fraction. Consider a solution containing two components, namely A and B. Here Xa and Xb are mole fractions of the component A and B respectively, where Na and Nb are the number of moles of the two components A and B respectively. Here the mole fraction of component A is given by Xa, which is equal to Na divided by Na plus Nb, and the mole fraction of component B is given by Xb, which is equal to Nb by Na plus Nb. Hence Xa plus Xb is equal to Na by Na plus Nb plus Nb by Na plus Nb. After simplification, we will get the value 1. Therefore, Xa plus Xb, which is equal to 1, or otherwise the mole fraction of A component plus mole fraction of B component is equal to 1. It is explained here. Here 0.5 mole of ethanol is mixed with 1.5 moles of water. Here the first component is ethanol, the second component is water. The number of moles of ethanol is 0.5 mole, where the number of moles of water is 1.5 moles. Here we have to calculate mole fraction of ethanol and mole fraction of water. First we will calculate the mole fraction of ethanol. From the above formula, mole fraction of ethanol is equal to number of moles of the ethanol divided by total number of moles of ethanol and water. Substitute the values in the above expression. We will get 0.5 divided by 1.5 plus 0.5, which is equal to 0.5 divided by 2, which is equal to 0.25. Hence, the mole fraction of ethanol is equal to 0.25. Next, we will calculate mole fraction of water. Mole fraction of water is equal to number of moles of water divided by total number of moles of ethanol and water. Substitute the values. We will get 1.5 divided by 2, which is equal to 0.75. Hence, the mole fraction of water is equal to 0.75. From the formula, Xa plus Xb equal to 1. Here, mole fraction of ethanol plus mole fraction of water is equal to 1. Since the mole fraction of ethanol is 0.25, the mole fraction of water is 0.75. Therefore, 0.25 plus 0.75, which is equal to 1. Next, we will discuss mass percentage. It is expressed as mass of the solute in gram divided by mass of solution in gram into 100. Neomycin aminoglycoside antibiotic cream contains 300 mg of neomycin sulfate, the active ingredient in 30 gram of ointment base. The mass percentage of neomycin is given by mass of the neomycin sulfate in gram divided by mass of solution in gram into 100. Substitute the values in the above expression. We will get 0.3 gram by 30 gram into 100. After simplification, we will get 1 percentage W by W. Here, the percentage W by W represents mass percentage. Next one, volume percentage. the volume percentage is expressed as volume of the solute in ml divided by volume of solution in ml into 100. It is explained here. 50 ml of tincture of benzoin and antiseptic solution contains 10 ml of benzoin. The volume percentage of benzoin is given by volume of the benzoin in ml divided by volume of solution in ml into 100. Substitute the values in the above expression. We will get 10 by 50 into 100, which is equal to 20 percentage V by V. Here the percentage V by V represents volume percentage. Next one, mass by volume percentage. The mass by volume percentage is expressed as mass of the solute in gram divided by volume of solution in ml into 100. It is explained here. A 60 ml of paracetamol pediatric oral suspension contains 3 gram of paracetamol. The mass percentage of paracetamol is given by mass of the paracetamol in gram divided by volume of solution in ml into 100. Substitute the values. We will get 3 by 60 into 100, which is equal to 5 percentage W by V. Here percentage W by V represents mass by volume percentage. Finally, we will discuss parts per million. The parts per million is expressed as number of parts of the component divided by total number of parts of all components into 10 to the power 6, which is equal to mass of the solute by mass of the solution into 10 to the power 6. It is explained here. 50 ml of tap water contains 20 mg of dissolved solids. The TDS value in ppm is mass of the dissolved solids divided by mass of the water into 10 to the power 6. Substitute the values in the above expression. We will get 20 into 10 to the power minus 3 gram divided by 50 gram into 10 to the power 6. After simplification, we will get 400 ppm. Here, the ppm represents parts per million. Hence, we completed the topic expressing concentration of solutions using different units. All the topics are very important. The concentration of a solution is expressed in different units. The choice of unit depends on the type of measurement applied. For example, in complexometric titrations involving EDTA. Hence, for this type of complexometric titration between EDTA and metal ion, molar solutions are used. Normal solutions are used for redox and neutralization titration. The mole fraction is used to calculate the partial pressure of gases and the vapor pressure of the solution. Percentage units are used to express the active ingredients present in therapeutics. ppm, that is parts per million, is used to express the quantity of solute present in small amount in solutions. Hence, it is clear that the solution with different concentration is expressed in different units. Let me stop up to this topic. The remaining that we will discuss in our next video class. Thank you.